Today we are going to discuss energy conversion and storage. Our speaker is Dr. Matthew Stokes from the Australian National University School of Engineering. Good evening, Dr. Stokes. How are you?
Doing well, thanks, Anna.
Dr. Stokes' research in renewable energy and photovoltaics spans more than 25 years. So he started really young. And his work with pumped hydro energy storage and integration of renewable energy here in Australia received the Eureka Prize for Environmental Science a few years ago. Is that correct?
Yes, with my colleagues, Bin Liu and Andrew Blakers.
All right. So, well, that's just a quick introduction. But Dr. Stokes, thanks for being with us here today, and the stage is yours.
Okay, thanks very much for that, Anna. So can I confirm that you can see my screen?
Yes, very clear.
So as Anna introduced, my interest is around the use of renewable energy. My background originally was in solar energy research, but increasingly I've been focused on integration of large amounts of renewable energy into electricity grids, and then the use of renewable energy to then decarbonize other sectors. So what I'll be doing today is taking you through the high level of the sorts of things that I've been involved with and continue to be involved with from a research perspective. So what I'll talk to you about first is changes coming. So what the drivers are for change and what's happening around energy in the world. Then talk to you about the leading technologies when it comes to renewable energy around solar and wind. And then speak to you around the challenges and what's needed to transition towards 100% renewable electricity. And then take the next step around what would it look like to start to look at 100% not just renewable electricity, but 100% renewable energy. So the first part is changes coming. And if global warming wasn't an issue, then it would be really hard to see the drivers for change that we're seeing at the moment. A lot of the issues around the use of coal, oil and gas are relatively benign in terms of the impact on the environment and the way the technologies have changed over time in good, mature economies. So issues around pollution or issues around degradation associated with mining are largely manageable. But what we're really seeing is a drive which is driven by climate change and that the presence of the CO2 that burning fossil fuels introduces into the atmosphere is not something which is sustainable, and that there's a need for change. And that need for change is accepted broadly. If you have a look at this chart up at the top left, what we're looking at here is analysis by the International Energy Agency around what are the sorts of changes that are needed to achieve net zero energy emissions in 2050. So while we have an energy mix at the moment, which is dominated by fossil fuels through coal, oil, and gas, what we see is increasingly moving forward, and this is just looking even as far as 2030, is a system which is dominated by introduction of new renewable energy, and we're going to be seeing the retirement of, particularly in the early years, coal and oil. Coal coming out of the electricity system and oil hopefully coming out of the transport sector. And this is not just a government thinking, this is something that industry is thinking about as well. So BP releases its energy outlook each year, looking at what it believes the future is going to bring. And it also is recognizing that there's going to be a rapid change towards electricity systems dominated by wind and solar, and coal and natural gas are going to start to disappear from our electricity systems. And that change is happening already. So we see that in terms of the annual deployment of new electricity generation, what we're seeing is that solar PV is already the largest source of new electricity generation, with wind sitting at number 2. And the fossil fuel generators are either stagnant when it comes to gas, or we're seeing a decline in terms of things like coal, and also with other technologies like hydro due to the environmental challenges with damming rivers and the challenges with nuclear around managing nuclear waste. So we're really seeing PV and wind are the 2 dominant technologies in terms of the change we're going to be seeing in electricity systems going forward. So what I'm going to do first is go through solar energy, but from a slightly different angle from those who saw Kylie's presentation last week. The first part of it, though, is whenever you're looking at an energy system, the first thing you want to know is, what is my energy resource? What is the energy resource I can use to convert into something useful? And obviously solar insolation is the metric that we're using when we think about solar energy. So what you see around the world is a general trend of, when you're closer to the equator, we see more sunshine, we see longer sunshine hours, more intense solar radiation. And as we move towards the poles, the radiation decreases. And so we see a situation where the solar resource is generally better towards the equator and generally gets worse as we move further and further away from the equator. What's important to recognise within here is that this is a vast resource and a resource that we're never going to deplete. Any one of these dots that you see on the screen is the area that we would need to cover in solar panels in order to meet the world's total electricity demand. So any one of these locations would have enough electricity generated from solar energy to completely meet the demand today. And then if we want to start to transition to other sectors that we're going to look at, trying to electrify transport, metal processing, any of these other areas, then we still have a vast resource available to support that transition. So when we think about the resource for solar photovoltaics or solar cells, then what we're interested in is not just the light that comes directly from the sun, but we're also interested in all of the light that comes from the rest of the sky and even is reflected off other surfaces. And so this is referred to as global irradiance. And so the global horizontal irradiance is the amount of energy that you would get if you lay a solar panel on its back. And you can see, if you zoom into Australia, we're seeing those same sort of trends, that generally we're seeing this resource decreasing as we move further south. But then there's also other overlying weather effects that we're seeing because of the monsoons in the north and the general more higher rainfalls in the east. We see the solar resource is reduced. But even when we have a look at this, what we're seeing is a variation of only a factor of 2 in the resource from the very best locations in Australia down to the very worst locations. That we're seeing only a factor of 2 difference. And because of the way that solar works, that means that we get basically exactly half as much energy if we would put a solar panel down in the bottom of Tasmania versus if we would put it into the sunniest parts of the Pilbara. Now, solar photovoltaics is different to every other way that we make electricity, in that it has absolutely no moving parts. So most generation technologies, whether we're looking at coal generation, nuclear generation, hydro generation, generation from wind, all of these technologies rely on a moving generator. And photovoltaics is different in that what we're doing is we're directly converting sunlight into the electricity, and that the sunlight that is entering the material is converted into a usable work. And the way that that happens is we rely on the fact that we have these materials referred to as semiconductors, which I'm sure many of you are familiar with, where there requires a certain amount of energy to get an electron that was bound to the crystal from the crystalline state into a more energetic state. So sunshine that comes into the material, breaks an electron free. That electron is free to move around inside of the semiconductor. But we also produce this counterpart, which is what's referred to as a hole, or a positive charge where that electron came from. And both of these can move freely within the device. The electron, you can imagine, would just move as it would in a metal, but the hole moves by the opposite effect, and that is that an electron nearby will jump into where that hole is, and where that hole was, we now have, sorry, where that electron was, we will now have a hole. So a hole moves around by this electron hopping in the opposite direction to fill the holes in where the electron was missing, while this electron is free to move within the device. So if we can create a structure by modifying our semiconductor so that part of the material has a negative charge, part of it has a positive charge, then these get attracted to one side or the other, and we can separate them and get them to do useful work by transferring into an external circuit. Probably shouldn't include a light bulb in it, because generally we're not going to be using a light bulb to be doing that, given that the sun is shining at that particular moment. But the idea is that we can extract these electrons and holes from contacts on the device and get them to do some useful work in an external circuit. So when we have a look at the solar resource, the vast majority of solar cells produced today are made from silicon. So silicon is a very abundant material in the Earth's crust. And so it's a material which we have no issues in terms of resource availability. Interestingly, though, we have a tension within that around, there are two dominant technologies which are leading the charge when it comes to solar production. And that is what's referred to as monocrystalline silicon or single crystal silicon. And this is exactly the same material that you would have in your computer chips or in your mobile phone. It's that perfect single crystal of silicon, which enables us to produce very high efficiency devices. But we also have a mix of materials which are referred to as multicrystalline materials, which is what you see on these sorts of solar cells, where you sort of see this random structure of crystals forming. And these two technologies have been fighting it out for market share, with the swing between the advantage of lower price for multicrystalline and the lower trading off against the lower efficiency. So the silicon wafers that we put into solar cells are the most pure material that's standardly manufactured by man. Impurity levels are typically less than 1 part per billion in the semiconductor, because any impurities that we introduce into that modify the behavior of our semiconductor. So sometimes we very deliberately introduce impurities to modify the behavior, to make it N-type or P-type. For example, introducing boron to introduce a shortage of electrons, or introducing phosphorus to create an excess of electrons. But generally, we want to have absolutely no impurities within these devices. So we start off with a hyperpure silicon. So this is a material that has been taken raw sand, stripped the oxygen off it, and then been purified through a chemical process. And then we melt that within a quartz crucible, so a silicon dioxide crucible, so again, to minimize contamination. And then we introduce a seed crystal. We just have a crystal of silicon, which we have a known orientation, and we dip it into that melt. And then when we slowly withdraw it from the melt, what we can do is grow a single large crystal of silicon from that melt. And so we might produce a single crystal that is something like 200 millimeters in diameter and several meters long, all with perfect crystal orientation. Every atom knows exactly where every other atom is within that structure. And we can then cut that ingot up into individual wafers, and we can process that into our solar cells. The approach with multicrystalline silicon is a little bit different. So rather than trying to produce this perfect single crystal, what we do is we take our silicon chunks and we put it into a square crucible instead, and we simply melt the silicon, and then we slowly cool it down over time. So there's no seed, nothing to provide that background information as to how it should grow. They would just get a random collection of grains forming as the material cools down. And so what we get there is this material which looks something like this, where we get these grains which might be of the order of several millimeters to centimeters in size. The material within the individual grains is really high quality, but then there are defects and impurities associated with the very grain boundaries in between these. So the efficiency of these devices is always going to be higher than the efficiency of these devices. So there's lots of work going on around the world looking at how to maximize the performance that we can get from these materials in terms of managing the impurities, improving the growth to get the best possible solar cells that we can. And then we have to go through a process of turning those silicon wafers into solar cells. And so when you see a typical solar cell, what you're seeing is a fairly consistent collection of features which are common to many solar cells. First, the blue color. So the blue color that you see on there is an anti-reflection coating. So an anti-reflection coating is introduced to solar cells to minimize the amount of reflection or to maximize the amount of light that we get into the devices. And the blue color is about getting the balance to get the most amount of infrared light and visible light that we can into our solar cell. As well as that blue color, what we also do is we actually roughen the surface of the devices. We do a process called texturing, where we roughen the surface, which encourages light to get into the silicon better, but it also means that the light bounces around inside the silicon multiple times before it escapes. So we need to use less silicon to produce the same efficiency. We need to introduce contacts. So on the front side of the solar cell, we need to introduce contacts so that we can both get the electrons out of our solar cell, but also minimize the amount of light that's reflected off of that front surface. So we've got this trade-off between the amount of area that we cover with our metal contacts to minimize the amount of reflection, but we also want to have enough metal that we can get that those electrons out without much resistance loss. And we also have to undertake processes which deliberately change the electrical properties of our solar cells. So the basic material typically has an impurity called boron introduced into it, or possibly gallium, to make to have a shortage of electrons in this part of the device. And then we introduce phosphorus into other parts of the device, typically at very high temperatures, 800, 900, 1100 degrees, so that those impurities diffuse in and we end up with regions that are negatively doped. And these help to separate our electrons and our holes from each other. Now, this is obviously a process that's been evolving over decades. The solar cells that were currently in larger scale production and the most efficiency devices being produced at mass scale at the moment are the PERC solar cells. And these were actually invented at the University of New South Wales by Martin Green, but also by Professor Andrew Blakers, who continues to do research here at the Australian National University into high efficiency devices. But we can also play around with different devices around reducing reflection by taking the metal contacts off the front side and introducing them onto the rear side of the devices so that we see no metal fingers on the front side, trading off complexity, an increasingly complex manufacturing process versus the efficiency improvements that we can achieve from those devices. So when it comes to PV factories, what we're seeing now is that these are very highly automated facilities. So typically we're making solar cells around about 156 by 156 millimeters, produce a few watts of power. A typical factory would be churning these through at roughly the rate of one per second. So very high throughput of these relatively large area devices. In terms of then the modules, what we're then looking at is factories producing something in the order of 600,000 modules per year. So we're now moving into a regime where the system is dominated by automation, and we're trying to standardize the processes as much as we can to try and decrease the cost of manufacture, increase the yield, and minimize those manufacturing costs. So it also means that the opportunities are not just around the renewable energy deployment, but the need for good engineers who are capable of managing the automation processes and making this process more and more efficient and increasing the throughput. So one of the things that's been really driving the success of solar photovoltaics is this idea of learning. And so there's this learning curve which are established for a whole range of different technologies, whether it be semiconductor manufacturing or manufacturing of cars. There's this idea that as we make things, we get better at making them. And when we get better at making them, they get cheaper. When things get cheaper, people want to buy more, and therefore we make more things. And what people discovered was that typically there is a relationship between how much we've made of something and how cheap it becomes to make it. That as we make more and more of something, what we find is that we get better and better at making it, get more efficient, more clever about the things that we can do, and the cost decreases over time. And silicon has been on a very amazing trend of over the last several decades of continuous increase in production rates and a continuous decrease, or almost continuous decrease in costs. And so if we look at the cost of a solar panel today relative to the price of a solar panel back in the early 80s, there's been more than a factor of 500 decrease in the cost of those solar panels. What's been interesting there, though, is that after a period where learning slowed down because of the cost of silicon wafers, the cost of silicon wafers got really high because demand got too high. Once we started to manufacture a lot more silicon and meet the demand of this, the silicon wafers, there's been an even more rapid decrease in the cost of each module. And so what we're seeing here is this amazing decrease, which is driving the growth of solar, which means it's now making a significant contribution to the overall world. But what that means is that we still need to do more learning. We need to get better at making our solar cells. How can we increase the efficiency further? How can we reduce the costs? How can we increase the performance? How can we increase the yield? So there's great opportunities in industry and in research to continue to drive that process. And as a result of that process, what we're seeing now is that the solar is now the leading technology in terms of new energy deployment. And the International Energy Agency has been a bit slow coming to the party. Their forecasts have been always well behind what the reality has been in terms of how quickly solar deployed. They kept predicting rates of deployment which were much less than what were actually being achieved. But they're now recognizing that solar PV is the dominant source of new electricity and will continue to be going forward. And the reason for that is that if you have a really good solar resource and you can get the solar financing right, and that is that you can access low-cost financing, solar PV is now the cheapest source of electricity in history. So it's now cheaper than coal, cheaper than gas, cheaper than nuclear, cheaper than wind. It is the lowest cost source of electricity. And so there's now going to be a natural drive towards people deploying solar simply because it's the cheapest technology, not just because it's an environmentally friendly technology. So what I'll do now is we'll touch on wind. So what we're looking at in terms of wind energy is a similar but a slower journey than what we've been seeing for solar photovoltaics. So wind has cumulatively more than 700 gigawatts has been installed around the world, with a record 90 gigawatts installed in 2020. And to give you a sense of the scale, that's $300 billion of investment in 2020. So this is not a small scale industry. This is a large, globally significant industry. And the World Wind Energy Council is forecasting that that's going to continue going forward, that there's going to be this 15% of that order per year growth over the coming decade due to a combination of improving economics and continued focus on global environmental goals. And if you go into the data, what we're seeing now is that wind has increased to around about 5% of total electricity generation around the world. So it's now making a significant contribution to the overall energy mix. So wind energy can be thought of as an indirect source of solar. So solar is the driver of wind around the world. So if we imagine the sunshine coming in onto the world, what you're finding is that there's more solar radiation hits each surface closer to the equator than it does at the pole, simply because of the cosine angle, that there's just less area facing directly towards the sun. And so as a result of that, we see a temperature difference between the equator and the poles. And so there's a natural drive for those two to equilibrate. So hot air rises at the equator and wants to move towards the pole. And then there's a counterflow where that cold air wants to return to the, to move to the equator to balance out that temperature difference. And what we see as a result of that is, because the Earth is rotating, we see different winds evolving at different latitudes. So when you're right at the equator, there's almost no wind at all. As you move away to the equator through the tropics, what you start to see is easterly winds, but relatively weak winds. But then as we move towards the mid-latitudes, what we start to see is the wind starts to shift to the opposite direction, and we see a predominantly westerly winds. So if we look at a map of the world around global wind resources, we see an almost perfect opposite to what we see with the solar resources. So close to the equator, we see relatively low winds, okay, because the rotation effects of the Earth don't have an impact and don't drive winds. And then as we move away from the equator, we see this general trend of increasing wind, with the strongest winds as we start to move towards those mid-latitudes. But the story is a little bit more complicated, because we also have interactions of topography, that areas of high elevation, so you see here that the Himalayas or the Andes, we see areas that are elevated get up into higher wind levels, and the higher you generally get stronger winds. So as well as that general effect of better wind as we move away from the poles, we also get these localized effects due to the presence of mountain ranges. And we can also get localized effects due to sea breezes. So an area here, the Arabian Gulf, we see much stronger winds than we would otherwise expected, simply because of hot air rising and the winds coming in to replace that hot air on the land from sea breezes. So when it looks to try and then understand that wind resource and how it's useful, we need to understand how we can extract energy from the wind. And so when you consider the standard wind turbine design, where we have typically these large 3 blades, then what we can do is we can extract energy from the area that those blades sweep through. And so the amount of energy that we can extract from a wind turbine is given by its area, by the density of the air, by an efficiency factor, and then by the velocity cubed. So it's important to note here that the energy from a wind turbine is proportional to the velocity cubed. So if I can double the amount of wind that I have in a location, I can get 8 times as much power out of the wind from that location. So unlike solar, where we have a nice simple relationship where there's a 1-to-1 relationship, if I double the amount of sunlight, I'm going to double the amount of energy I get from the wind, sorry, from my solar panels. What we're seeing with wind is that we're seeing this cubic relationship. And so because of this cubic relationship, it's really very sensitive to the amount of wind that we have available. And therefore, what we find with wind data is it's much more challenging to determine a good wind site, and we do much more measurement and much more development before we go through a process of developing a wind energy site. And what we do when we design a wind turbine is also that we don't use that cubic relationship for the entire design of the wind turbine, is that we limit the power that particular wind turbine can produce. And the reason we do that is if we have really, really strong winds in a location, then we're going to introduce really, really high stresses on the turbine blades, and we're going to introduce high stresses on the generator and the gears. And so we deliberately limit the amount of power that we produce from a wind turbine. So we start off with at low to moderate winds, we see this cubic relationship, and then we slowly detune the wind turbine so that it's not producing that maximum power. And we actually deliberately make it less efficient. And that is to protect and to make the strength of the componentry doesn't have to be as high, to try and reduce costs. So when we're trying to work out how much energy we can get from a wind turbine, we need to go through a process of understanding what the wind resource is in that location. So it would be typical for a wind farm developer to go out and measure the wind resource, not just based on historic data, but to actually put up a tower and measure the wind for a year or more to try and understand if the resource is what we expect it to be, and then combine it with the wind turbines that they want to deploy to predict what the energy is going to be like, deployment is going to be like in that particular location. So you can imagine that this is a much more complicated process, requiring much more engineering skill and much more understanding of the relationships between wind and topography, etc. So a typical wind farm development might take 4 to 10 years from the idea of here's a good wind site to here's an executed wind turbine. Whereas a solar facility, it could be 12 months from here's the idea that I might want to do it here to it being fully connected and deployed in the grid. So hopefully I've given you a bit of a flavour for the 2 key technologies that we look at in terms of renewable energy systems moving forward. And what I'll start to talk to you about is 100% renewable electricity and thinkings in terms of that pathway. And Australia is a really interesting place to be doing this at the moment. If we look over the last 3 years, and probably what's going to be happening again this year, is Australia is leading the world in terms of the rate that we're deploying renewable energy, particularly PV and wind, on a per capita basis. So while the world average is around about 25 or 20 to 25 watts of new capacity per person, what we've been seeing in Australia is a rate around about 10 times that. We've been seeing around about 200 watts per person at deployment, which means we're experiencing a really rapid change in our electricity system. And this has been embraced by the industry. So just yesterday, the Australian Energy Market Operator had a new CEO, Daniel Westerman was appointed, and he is setting a goal for the Energy Market Operator to be able to design the system and have the system operating such that it's capable for short periods of time, not yet 100% of the time, but for short periods of time, operating at 100% renewable energy capacity. So all of the energy in the system would be coming from wind and solar. And this gives you a bit of a sense of the scale of the challenge that's involved in terms of thinking about this. So this is a particular state within Australia. This is South Australia. And this is a week's electricity generation. This is demand. This is 1 week of time, showing you the generation of wind and generation of solar energy in that week relative to the demand in South Australia. And so what we see here is a system which is really quite different to traditional electricity systems. What we see is potential for very high ramp rates as wind or solar turns off. There are times when the residual load that's not met by wind and solar is relatively low, through to other times when it can be almost the entirety of demand needs to be met by other sources. We can have periods of very low generation through to periods where there's more generation in the system than is needed to meet demand. There can be very rapid short-term variations, as well as regular daily trends where you see things like solar coming in and out of the system. So the energy system is going to have to behave very differently moving forward in order to enable high fractions of generation. But these things are eminently doable. So things that help are things like technical diversity, that we don't want to have just PV or just wind. We want to have a mix of those and ideally have other resources such as existing hydro and biomass to help support the system. We want to have things spread out widely. If we can have systems, wind generators spread apart a long distance, then we smooth out the effects of weather. The wind might be blowing in South Australia, for example, but not be blowing in Queensland. We can transmit energy from one location to another location using transmission systems. We also need to start to think much more hard about demand management. What are the sorts of loads that I can choose to turn on and off at different times of day? To benefit from low-cost solar energy, I might choose to heat water and store it in the middle of the day, whereas the old system probably would have been aiming to use the middle of the night when demand was low to heat water. We want to start to identify interruptible loads. What are the sorts of things that we can turn on when energy is cheap and available, and what are the sorts of things that we might turn off if energy is in shortage? And then finally, if your system, if you've exhausted these sorts of approaches, then eventually you want to move to storage. But storage is the last thing that you want to be doing. Storage is expensive and fundamentally is just a process that is being used to try and shift energy from one time period to another. So the two leading technologies there are going to be batteries and pumped hydro energy storage. So when it comes to transmission, technology has come forward in leaps and bounds. China has recently commissioned a high voltage DC transmission line, which is more than 3,000 kilometres long, being able to move energy from the areas of rich resources for solar and wind in the west of China, all the way to the East Coast demand centre, some 3,000 kilometres. Very, very high voltage. We're now talking high voltage DC systems having 1.1 million volt systems. So incredible engineering to manage those sorts of and develop those sorts of voltages, and very high amounts of power. So 12 gigawatts, for context, is about a third of Australia's peak energy demand is being shifted by this one power line in China. So we're capable of moving very large amounts of power through these systems, which then helps to average out the effects of weather across large electricity systems. When it comes to storage, then battery storage is likely to have a very large contribution when it comes to power. So the electronics associated with delivering power for battery systems is really very, very cheap, something in the order of $150 a watt to deliver power. Whereas the energy component, the battery cells, are where the energy is relatively expensive. So on a per kilowatt basis, batteries are cheap, and on a per kilowatt hour basis, they're relatively expensive. But also at this stage, battery systems are relatively small. So the largest battery system in the world connected to a grid was the Tesla Big Battery, or the Hornsdale Power Reserve in South Australia. And to give you a sense in that overall week in terms of power and energy, in terms of time, this gives you a sense of the size of what that battery contributes in that system. It's had a really important role in terms of managing the fluctuations in the system. So you can actually see patches of blue in this system. This is where the battery is either injecting power or extracting power from the system to help maintain the stability of the system. but it's not doing a lot of work in terms of energy balance. In contrast, Australia is building Snowy 2.0. This is a large pumped hydro scheme in New South Wales, Victoria. This will have enough energy capacity to store the entirety of South Australia grid for a week. Yeah, so we've just got several orders of magnitude, probably 3 orders of magnitude difference in terms of the energy storage capability of pumped hydro and batteries. So they're going to play really important complementary roles in the system moving forward, and working out how to make them play well together is going to be an important part of the challenge. What's also important is identifying where we can deploy these systems. Obviously, a battery we can deploy anywhere, but pumped hydro depends on being able to have 2 reservoirs, one reservoir high up in the hills and another reservoir down in a reservoir valley. So some of the sort of research work that we've been doing here at ANU is developing a global atlas. Feel free to follow the links afterwards, and you can zoom into your favorite site where we can identify where potential pumped hydro resources are around the world. And importantly, there are orders of magnitude more than are required to balance 100% future electricity system, whether that's in China, in India, through Southeast Asia, in the South Americas. There's a vast overabundance of pumped hydro sites to support the storage needs. So if we get to the point where we have a 100% renewable electricity system, then we can leverage off of that to look then at 100% renewable energy. Electricity is a really powerful tool to be able to shift energy into other sectors because it's in a form that's very easily movable into work. So if I take an Australian focus to begin with, then looking at Australia, about 1/3 of our total emissions are electricity. And then we have emissions from land transport, low temperature heat, high temperature heat, aviation, industrial sectors, agriculture, and fugitive emissions associated with mining. And the vast majority of these we can directly electrify. The mining emissions will disappear as we decrease our fossil fuel uses, but the rest of these energy sectors can be increasingly supplied by electricity. So transport's the natural next spot for things to occur. Electric vehicles are already starting to take off around the world in terms of very high growth rates, with the big advantage is that these have very, very low running costs. Electricity is a really efficient way of transforming energy into motion. Typical battery electricity through to motion systems for electric vehicles are of the order of 80%. Whereas if I'm looking at the efficiency of fossil fuels from embodied energy through to delivered transport, we're looking at the order of 10 to 20%. So there's a huge reduction in the amount of energy we need if we electrify transport. And it's not just electric vehicles. We're also seeing increasingly announcements around heavy transport. So Tesla developing its semi, but there's also shifts into other sectors, where both aviation for relatively small planes, but also for shipping. In this case, Norway have developed a ferry that's fully electrified for car transport. Low temperature heat, we see similar advantages that we see in transport, in that we can use electric heat pumps to transport electricity through to low temperature heat. And the advantage there is that for every unit of electricity that we put into the system, we're getting 3 to 5 units of usable heat out of the system, that we're taking the heat from the outside system and transferring it into the delivery system. Heat pumps are good for temperatures up to around about 150 degrees if we're losing multiple stages, or if we're using a low temperature waste heat stream to be able to take that low temperature heat through to temperatures of the order of 150 degrees. And we can also then couple these systems with thermal storage so that we can use the heat pumps when we have an excess of energy in the system to transfer heat from into the system at times when energy is lower cost. In other sectors, we're increasingly starting to look at hydrogen as a method for energy in decarbonised systems. And when we're looking at hydrogen, we can directly produce hydrogen from electrolysis from renewable energy, that we can use that energy to split water into hydrogen and oxygen, and then use that transfer to be able to move energy use into low carbon options. So steps here include just direct gas replacement. So if you're looking at the Australian context, there's an opportunity of displacing more than 29 million tonnes of exports of CO2 into hydrogen use. But importantly, hydrogen then is also a chemical vector which can replace carbon for reduction of metal processing. So in steel production, we could be potentially using hydrogen to strip the oxygen off of iron to be able to produce iron directly from electricity production. Fertilizers are a huge user of hydrogen. So if we can introduce clean hydrogen into the system, the production of ammonia can also be made clean. And there's increasing interest around the world, including Australia having several announcements of 100% renewably electricity driven processes, as well as potential for hydrogen to be part of the automotive industry, where you're looking for long range, or you're looking for energy which is, for transport which is decoupled from the grid. Then hydrogen via fuel cells could potentially be a big market for decarbonisation. But when we talk about these things, there's still huge research opportunities in these different areas. So iron and steel in particular, we don't have yet a proven economically competitive way of using renewable energy to convert iron ore through to usable steel. So there's lots of ideas around how we can use renewable energy to undertake some of the early processing of ores, to potentially use it either as direct reduction from iron, electrochemical processes, electrowinning. There's no clear winner yet in terms of what the technologies are that we're going to be able to use to attack what's a very significant part of the global energy emissions mix, with steel and iron making up 7% of the global energy mix. But we do have technologies around the use of electricity directly to process iron through into usable products through electrical arc furnaces. So in summary, what I've hopefully taken you through the idea of is that we're on the absolute cusp of a massive energy change, and that's driven by the need to decarbonise our energy sectors. Wind and solar are emerging as the dominant new electricity supply technologies, and they're really nicely complementary, that the areas with good solar tend to have lower wind, and the area with good wind tend to have not as good as solar. But we can also move energy from one location to another, supported by long distance transmission. But there is still lots of work to be done in terms of transforming our grids to cope with lots of wind and solar. Grids are going to have to operate differently in terms of being able to respond to the fact that wind and solar are intermittent, and we get our energy when the weather conditions permit. And so the grid is going to need to operate differently in terms of integrating storage, demand management, and different grid design to be able to operate reliably. But once we have a low emissions electricity grid, we're now going to enable low emissions energy in other sectors and enable decarbonisation of these other energy sectors. So all of this is going to happen over the coming decades. So there's going to be no question, there's going to be lots of work for capable engineers in the coming decades. So ANU is largely a research-led university, but we do have a strong teaching program that builds on our research strengths. So if you do have interest in continuing studying at the ANU, then we have Bachelors of Engineering in Renewable Energy, Master's courses in Renewable Energy, but also a Master's course in Energy Change, looking at the broader aspects of the energy system, with not just an engineering focus, but also a policy, social science aspects of the energy transition. So have a look at those programs if they're of interest, if you're interested in expanding your education opportunities through the ANU. So that's a very high level pass through. This is the space that I'm undertaking research in and my interests. There is lots of activities here at the Australian National University around energy change. We have more than 150 individual researchers who are working in the energy space. with several $100 million of infrastructure and support for those sorts of activities. So if you're interested in reaching out, feel free to contact Anna or myself with my contact details there. But I'll also throw the opportunity open for people to ask questions via the chat if you have any that you'd like to explore. So thanks very much for your attention.
Thank you so much, Dr. Stokes. And if you have any questions, please just drop them on the Q&A button on the bottom of your screen, and we are going to address them. I was very impressed about your presentation. And one of the things that I was thinking, I'm glad you mentioned in the end the different options for people to study, but I was thinking that all this change, it's not only in renewable energy, but there's so many branches of engineering that can be involved, and also so many branches of other sciences as well that will have to, that have opportunities for people to work on, right? Do you see some sectors that will be growing very quickly because of this development of renewable energy?
Absolutely. So you can see that in the development of smart grids, for example. So there's an increase deployment of generation at household level. So people are deploying solar at households, they're deploying batteries. So managing these systems is also going to be a challenge moving forward. So having the control systems to be able to work with in these systems, to be able to have the IT interactions so that you can actually have trade of electricity between consumers. All of these sorts of aspects are going to be developed. So the IT support, control engineering, the material science, there's a whole range of other engineering disciplines that are going to be part of this energy transition, which is going to be a multi-trillion-dollar exercise over the coming decades.
And do we have the amount of professionals that we need to actually develop this sector as much as it can be developed?
Never. And the reality is that these industries are growing and growing rapidly. What I talked to you about in terms of solar growing at 30% per year, there is just a continuous need for people with engineering skills to be able to support manufacturing processes, deployment processes, integration in grids. I think you would have seen in the quote that I saw from AEMO that they're looking for all of the expertise that's going to be needed to be able to operate the electricity systems of the future as we change our electricity systems dramatically in the coming years.
And you showed us a few graphics that show the rapid growth in Australia and also around the world. Which countries would you say that are leading this change towards renewable electricity and renewable energy?
So it's distributed quite widely around the world. There are some obvious candidates. So Germany and the USA, they were some of the early leaders in terms of technology, and Japan, but increasingly China and India are also making a huge role. So in an absolute value, rather than a per capita basis, China and India are leading the world in terms of solar energy deployment. So the biggest markets in the world are sitting there and supported by governments that recognise the need for change, that the electricity system is no longer going to be dominated by coal and gas moving forward, and that there's a need for deployment of solar and wind to enable that electricity systems to grow and to support the economic development that those regions have been experiencing.
There has been a lot of discussion on how feasible it is to turn into a completely, to turn the world into working on completely renewable energy. And we've seen people in different, positions of power saying that it's possible or that it's not possible. But from the technology perspective, it seems very possible to do it and quickly.
Yes, so increasingly it's not only is the technology capable, but the economics is there. If you look at modelling 100% renewable scenarios in Australia or elsewhere in the world, it's relatively easy to demonstrate that with the right mix of generation and storage, transmission, that you could meet any potential future demand. But what's important with it as well is that the costs are coming down. So the costs of solar, the costs of wind, the costs of batteries the cost of control systems, the IT support, all of these things are also happening. So the decisions are not just being made on environmental grounds, that increasingly people are deploying these technologies because they are the cheapest technology. And so that's where, again, I'd look at the quote around the IEA. Solar is now the cheapest source of electricity. Now, that doesn't necessarily mean it's usable in terms of when you want it, but in terms of the raw energy source, it's now the cheapest. So working out how to best use that cheap energy is going to be really important for us moving forward. But the technologies exist. What we need to do now is be really clever about how we deploy them and roll them out to ensure we continue to meet the sort of climate targets that the world is setting.
So what can the people that are watching today, or the people that are going to watch later on the website, what can you do as an individual to help on this transformation? I do believe that maybe, you know, learning more about renewable energies and the technologies can be a very good step. But what can we do in our as individuals to help that?
So follow your passion. So find what it is that motivates you, and that makes life a lot easier in terms of justifying what it is that you want to do. So if you're really interested in materials, then there's lots of opportunities to make a difference in materials, new battery anodes, the next generation of solar technology. How do I make a recyclable wind turbine? There is a whole collection of things that material scientists can focus on. If I'm a control scientist, how can I make sure that my wind turbine is responding to changes in the grid such that the system stays stable and reliable? That my battery in a consumer's household is operating in such a way that the household is getting the maximum benefit from that battery, and only using energy when prices are high and not when prices are low. If I'm interested in the engineering behind electricity transmission, then getting involved in development of high voltage DC or better transformers. So there are so many ways that people can, from an engineering background, can get involved in the energy transition and find the niche that they really enjoy.
All right, thank you so much. Dr. Stocks, I believe that's it for today, and I really appreciate your participation. It was a great presentation, and I hope that our attendees have enjoyed it as well. Thank you so much.